Okay, welcome to PreCalc, Appendix A3, or Appendix 3. We have it as a delimiter A3. I will be able to, after this section, identify the domain of an algebraic expression, reduce rational expressions, and perform operations with rational expressions. Simplify so that's what I'm going to be able to do. Let's see what we've got. Okay, first thing we've got going. Domain of an algebraic function, fractional expressions. A fraction is a quotient of two algebraic expressions. Rational expression, an expression that can be written as a ratio of two polynomials. Now, this fractional expression, okay, it's a fractional expression, but it is not a rational expression because this is not a polynomial. Okay, that square root would exclude it from being a polynomial. This is the connection of two polynomials in a fractional expression. That is a rational expression. Unlike polynomials, which are defined for all real numbers, some algebraic expressions are not defined for some real numbers. Okay? The domain of the algebraic expression is the set of real numbers for which the algebraic expression is defined. Now, in example 1, finding domains of algebraic expressions. In this case, there's no restriction on the domain here because I don't have a fraction. I don't have any limitations as I would with a fraction or, say, a square root. So when we're talking about domains of an algebraic expression, I'm talking about what values I can put in for it to work all the time. Okay, well, in this case, the domain is all real numbers. Now, a lot of times you've seen it written like this, but if I write it as a set builder notation, I said x such that negative infinity is less than x, which is less than infinity. Okay? But then another way to look at it is an interval notation where I can talk about it as from negative infinity to infinity is the domain. So any one of these threes is acceptable to talk about the domain. In B, I have a restriction on the domain because when I'm doing this, the value inside can't be negative. So I can't have my value be my x minus 1 must be greater than or equal to 0. Okay, well, I'm going to solve this and find out that x must be greater than or equal to 1. Well, after doing that, now my domain is x such that x is greater than or equal to 1. Okay, and if I put it in set builder, it'll be that way. If I put it in interval notation, it'll be closed, unbounded, because it'll be closed at 1 and go up to infinity. In this next one, in C, the restriction is that I cannot divide by 0. So I've got to wonder, when's x going to be 0? So here, x minus 2 is 0 when x is 2, if I solve it that way. Oh, let's not do it like that. When x is 2. Okay, so after I know that's when x is 2, my restrictions for my domain is when it's not. Okay, so now my domain for x such that x can't be 2. Well, if I've got that written in set builder notation, if I write it as interval notation, I go from negative infinity to 2, union 2 to infinity, because it's open here at 2. Reducing rational expressions. Factor the numbers and denominator into prime factors. Simplify the expression by removing common prime factors and include the restrictions on the domain from the original expression. Now this is important. The domains is from the original expression. And we're going to be talking about removable discontinuities and that with this. But keep that in mind. We're going to be getting to that, but for right now, all our domains are based on the original expression. So let's factor first. In this first one, I can take an x out, and I have this as the difference of two squares. So x times x minus 3 and x plus 3, x minus 3. I've factored this out. X comes out of both, and this is the difference of two squares, x plus 3, x minus 3. Well, I can factor out at x minus 3. So x over x plus 3 is my solution for reducing the rational expression. But when I start talking about the restrictions on the domain, I go back to the original. And it's easiest for me to see this, and it's everything in the bottom. I just can't have x equal negative 3 because that'll make this 0, or x equal 3 because that'll make this 0. So that's what my restrictions are. Now, I've gotten it written pretty simply here, but if I put it in set builder notation, the set x such that x is not 3 or negative 3, or if I do it in interval notation, from negative infinity to negative 3, union, it's open from negative 3 to 3, open, and open from 3 to infinity, unbounded. So keep that in mind, the two different ways I can write my domain using set builder and interval notation. The first thing I got to do, I look at the problem and I go for factoring it. So x minus 6, x plus 3. Negative 6 and 3, got those. This is 2x up front. A 3's got to be here and a 1 here. So I've got 2x minus 1, x plus 3. And now the x plus 3's will cancel out. They become 1. So I can get this down to x minus 6 over 2x minus 1, reducing it. But my domain is based on the original problem. So because of that, I've got to solve 2x minus 1 when it's going to be 0 or not 0. So 2x minus 1 is equal to 0 when it's a half. So I can't have it be a half. And then x can't be negative 3. So I have it can't be a half and it can't be negative 3. So I'll write this in interval notation. In interval notation, I'm going from negative infinity to negative 3. And remember, it can't be negative 3. It can be around negative 3. So it's union from open from negative 3 to a half. It can't be a half. It can be around a half. And open from a half through infinity. So that we've got set builder and interval notation. I don't care which one you choose. I'm going to be honest with you. The more restrictions you have, the easier it is to use the set builder notation. Now, two rational expressions are equivalent if they have the same domain and have the same value for all numbers in the domain. The reduced form of the rational expression must have the same domain as the original expression. Now, a little hearkening back to the geometry, two fractions are equal, u over v equals z over w, if and only if uw, their cross product, vz, are the same. Okay, so let operations with fractions, let u, v, w, and z be real numbers. Variables are algebraic expressions. All the denominators are assumed to be different from 0, so none of them are 0 here. So if I go u over v plus w over v, u plus w over v. Fraction, denominators are the same, add the numerator. So if the denominators are different, I have to get a like or a common denominator. So I got to multiply the top and bottom of this one by z and the top and bottom of this one by v. And that's where I come up with uz plus vw over vz. If I'm multiplying, I don't have to have like denominators. So I just multiply straight across, numerator times numerator, denominator times denominator. And when I have a division by a fraction is the same as multiplying by that fraction's reciprocal. So that's why I can get away with uz times vw over here. For subtraction, replace the plus by a minus in 1 and 2, and you're golden because it's the same deal. So exchange these pluses with a minus here and a minus here, minus here and a minus there, and we've got subtraction covered. Now, just to emphasize these examples, we have numbers put in for each one for the addition when the denominators are the same, the addition when the denominators are different, multiplication, and then division, so you can check those out. Now, multiplying, dividing rational expressions. Factor them. Just factor what you've got. So let's factor what we got. I got 2x minus 3 and x plus 7 on top. On the bottom, I can take out an x, so it's x times x squared plus 2x plus 4. On this next one, it's a perfect cube. Remember the difference of two cubes? And where this is a minus and this other one's a plus, that's the pattern we had talked about. Okay, so now we got x squared plus 5x minus 14, which is x plus 7 and x minus 2. Now, x plus 7 will cross each other out, x minus 2 and x minus 2. So 2x minus 3 is on top, and I've got this x squared plus 2x plus 4 and out, so I got 2x minus 3 over x. That's what it reduces to. Now I have my restrictions. It can't be negative 7, can't be positive 2, and it can't be 0. And this will always be positive. So now we have x, our domain is x such that x cannot be negative 7, 2, or 0. Now it's your turn. Give it a try, factor them, but before you start, notice that this is a division and just rewrite it as you go. Well, we'll step you through. Remember, this is not a difference of two cubes, but a sum of two cubes, where the second one, it's x and 1, and x squared minus x plus 1 at the end. And then we're looking at factoring this, which is x plus 1 and x minus 2. And here I'm going to flip-flop this. This is going to factor and be on top. So it's x minus 2 squared, x minus 2, x minus 2. And this one is x squared minus 1 plus 1. I can't factor this anymore. So x squared minus x plus 1. That's it. That's all I can do. So now I've got x squared minus x plus 1 and x squared minus x. Those actually cancel out. I can actually knock those guys out, and maybe I'm going to get rid of those. Okay. These guys, one of these guys and one of these guys, and this guy knock each other out because that's 1 and that's 1. So it really comes down to factoring to x minus 2. But remember, the original domain, the domain goes with the original, so the domain, I can't have it be negative 1 or positive 2. And remember, this doesn't cross the axis because it's not factorable. So now we have the domain is x such that x can't be negative 1 or 2. Now, adding rational expressions. Remember, when I add rational expressions and they're different, I've got to multiply to find my like denominator. So I'm going to multiply this one by x minus 5 over x minus 5, and this one by 3x minus 2 over 3x minus 2. So able to get that done, x minus 5 over x minus 5, 3x minus 2 over 3x minus 2, and we have the same denominator. I combine like terms. Okay, this is x squared minus 5x. This is 9x minus 6. Okay, over 3x minus 2. So I've got my like terms. I got x squared plus 4x minus 6. And I've got 3x minus 2 and x minus 5. And now I look to see, can I factor this out at all? And, a number. And I'm looking for integer factors. Two numbers that'll multiply to be negative 6, but add to be 4. Add to be 4, multiply to be negative 6. I got 3 and 2. So this isn't going to be an integer, a nice clean integer function. So when I'm doing this, I've just got to solve this. This is my restriction, and this is x can't be 2/3, and x can't be 5. Same idea here, multiply. Oh, I don't have to multiply the top and bottom by anything because it's already there. So this is 2x minus 2 over x plus 5. So I've got 2x minus 2 over x plus 5. My restriction is x cannot be 5. Okay, and we're done. So we got that with number 4. And my last one, if the denominators of a fraction have common factors, then it's often more efficient to find the LCD before adding or subtracting the fractions. LCD, least common denominator, is the product of all the prime factors in the denominators, where each factor is raised to the greatest power found in any one denominator for that factor. So here, I'm going to look at this and I'm going to break these down. Okay, so I've got 2 over, I've factored out an x times the quantity x minus 2, times x minus 2, x plus 2. So now I'm going to get this set up, so I'm going to multiply by the LCD, least common denominator, to help me with this. I've got an x minus 2, x plus 2, so I need the x plus 2, so the x plus 2 over x plus 2. On this one, I'm going to multiply by x minus 2, x plus 2 on top, and x minus 2, x plus 2 on the bottom, so it becomes this. Remember, this times 1 is just this, and this whole thing with x. And I'm working with having like denominator, and somebody forgot a parenthesis over here. So let me get a parenthesis in there right there. And now this next one is minus 3x, because that was the only thing missing out of this to make it work. Now, at this point, I've got a denominator taken care of. I'm looking at my numerator, and I'm going to go after my numerator. Now I've got 2x plus 4, x squared minus 4 minus, x squared minus 4 because it's the difference of two squares, and minus 3x. Now I'm going to combine like terms in my next thing here. And I've got x squared, and I got negative 4 and 4, that's 0, and negative 3x and 2x, that's x. And now I'm going to look for my restrictions. Well, I suppose I can multiply these things out. I can take out an x. I got x minus 1, so there's not going to be too bad there, but I've got an x here and an x here, taking out that x, so they cancel. And write the following expression as a fraction or reduced form. And I've got this. But now, keep in mind, we've been doing domains. So I got to keep in mind, I'm working with a domain, and the domain is x such that x can't be negative 2, can't be 2, and can't be 0. Even if I go back to the original, it can't be 0 here, it can't be 2 here, and it can't be negative 2 over here. Well, it can't be 2 there, and it can't be negative 2 either. But as I break it up, without getting rid of anything, I can still find that same domain. Now, compound rational expressions. These are a little bit more involved. A compound fraction, aka complex fraction, has fractions for the numerator. Now, I have a situation like this, and there's a couple ways of looking at these. I can multiply the top and bottom by x plus 2 here, and minus 7, x plus 2, and top and bottom by x minus 3. And 1 x minus 3 over x minus 3 here. Okay, so I'm getting like denominators, and I'm going to combine the like terms. So I've got 3x plus 2 minus 7 over x plus 2, x minus 3 minus 1 over x minus 3. Now, this, remember, this is a fraction divided by another fraction, so it's the same as this fraction multiplied by this reciprocal. And that's where I'm going. I've got 3x plus 6 minus 7, x plus 2, times x minus 3 over x minus 4. Okay, now I can multiply this out and see about what's I've got 3x minus 1 on top times x minus 3, x plus 2 times x minus 4. Okay, so I can solve this fraction this way, or combine like terms I should say, not really solve. But I'm looking for the domain, and the domain x can't be negative 2 or 4, but back here in the original, x could not be negative 2 or 3. So when I'm doing this, I've got to make sure x, the set x such that x can't be negative 2, 3, or 4. Now, a new method to look at this is kind of involved. It's working with the idea of use the LCD to simplify the compound fraction. So I'm looking at this. I've got a squared, b squared on the bottom, and a and b. So I'm going to multiply both top and bottom by a squared, b squared over a squared, b squared. Why? Because this is the largest factor that'll be multiplied out, and when I do this, it's going to get rid of the a squared, it's going to get rid of the b squared. Here it's going to get rid of the a, and it's going to get rid of the b with things left over. I'm just multiplying by a form of 1. So when I do this, a squared b squared over this a squared becomes b squared, so that the a's cancel, and here a squared because the b squareds cancel, and over here I've got a b squared minus a squared b. So this is the difference of two squares on top Okay, and I can factor out an AB out of both of these in the bottom. So I get this situation. I got B plus A times B minus A over AB times B minus A. So that B minus A's can cross out, and on top I have B plus A over AB. Now, when I'm looking at this, I'm not going to have the restrictions that I normally would have. I just know that A can't be B, A can't be 0, and B can't be 0. Okay? So I'm just going to write those in as the domain. A and B can't be the same value, otherwise this will be 0 on the bottom. Now, what did I do? I looked at the problem and I looked at the denominators. Okay? This is x squared plus 2x plus 1. And remember, that's the perfect square of x plus 1. So if I go x plus 1 times x plus 1, top and bottom, squared, now x plus 1 squared, because it's a perfect square, because this is the perfect square, I'm able to get rid of that on the bottom, and it's going to be x cubed, x plus 1 on top. So I've got x cubed, x plus 1. This knocks this out completely, so it's just x. Now, the x's here I can factor out, so this is x squared times the quantity x plus 1. And now I look at my restrictions. And I know that x can't be negative 1. X can't be 0, because if this is 0, it makes this 0. And if this is 0, I can't divide by it. Okay? And I know that x can't be negative 1 here. So, as far as my restrictions are concerned, it can't be negative 1 and 0. Okay? Here, doesn't matter. And here, it says can't be 0, but here it can't be negative 1. So I've just got to make sure I go back to the original and make sure my domain is set. Now, extra practice for simplifying. Okay, again, this is x and y, so I multiply by xy, but I multiply by x squared, y squared to get rid of these. So now I'm going to multiply by x squared, y squared, top and bottom. And when I do that, this is going to be, and I'm going to go, this is going to be x cubed, y squared, but then the y is out, so it's x cubed y. This is going to be x squared y cubed divided by x, so it's xy cubed. This is going to be y squared, and this is going to be x squared when I'm done. Okay, now since I'm factoring, you got to keep in mind, I have to have a goal in mind, because sometimes people are like, well, how did you decide to do stuff? Well, right now, I've got x squared minus y squared up top. I was able to factor out an xy. I factored out an xy out of both of these, and I've got x squared, and if I factor out xy, I get y squared. If I look at this and factor out a negative 1, I get this. That negative 1 times the quantity x squared minus y squared. These are the same. So this will cancel this, or they become 1, and I've got xy over negative 1, which is this negative xy. Now I've got to look at my restrictions. X and y can't be the same. X can't be 0. And the reason why it can't be 0 as we go through here is x can't be 0 and y can't be 0. Because I go back to the original. Okay? So that's my domain right here. Okay, so now in AB, this looks like a division, but it's a plus sign. We've got 4y squared minus 9 all over 2y squared plus 9y minus 18, plus 2y squared plus y minus 3 all over y squared plus 5y minus 6. So I'm going to factor this 4y squared minus 9, and I've got 2y minus 3 times the quantity 2y minus plus 3. Here, it's 2y minus 3 times y plus 6. Over here, I have 2y plus 3 times y minus 1. And down here, I have y plus 1 times y minus 1. So we went through that factoring in Appendix 2. And because of that, we're able to get this Appendix 3 stuff done. But notice some stuff that's going to cancel. I got 2y3. And I use cancel pretty loosely. They're going to become 1. 2y minus 3 over 2y minus 3 is 1. And I've got y minus 1 and y minus 1. That's 1. So now I've got y plus 6 as the common denominator on the bottom. So I've got this situation where the denominator is the same, and I get to go 4y plus 6 all over y plus 6. Okay. Now, keep in mind, I can't have y be negative 6. I have a restriction on y because now I've got 2y minus 3 can't be 0, so y can't be 3 halves. Y can't be minus 6, and y can't be positive 1. This is a restriction where it can't be positive 1, so I got 3 halves, negative 6, and 1 as my restrictions on y in set builder notation. Remember, the more restrictions I have, the easier it is to write it in set builder notation versus interval notation. Now I've got two problems left here. I got 1 over x plus 5 plus 2 over x minus 3. Remember, to get like denominators, I've got to multiply the top and bottom of the saved value. So x minus 3 over x minus 3 and x plus 5 over x plus 5 is going to be multiplied out. So I have the same denominator in both sets, so I can combine like terms. And I'm going to distribute the 2, so it's 2x plus 5. 2x plus 10, excuse me, as I distribute that. And now I've got x minus 3 plus 2x plus 10 all over x plus 5 times x minus 3. Now, keep in mind, by combining like terms here, I'm going to be able to take and have 3x plus 7 on top all over x plus 5 times the quantity x minus 3 in the bottom. So I get to take this, and it reduces to this, or I should say they combine to this. And then I have restrictions that x can't be negative 5 and x can't be 3, just like the way it was at the beginning. So my domain for x, such that x cannot be 3 or negative 5. Now in 8D here, we have x squared minus x minus 20 divided by 2x squared plus 7x minus 4. We're going to factor the top and factor the bottom. The top is going to factor as x minus 5 times quantity x plus 4, x minus 5 times quantity x minus plus 4. And then on the bottom, we're going to have this factor. We're looking for a like factor, and it's going to be 2x minus 1 times the quantity x plus 4. So when we're doing this, we're looking at these, and x plus 4 and x plus 4 are going to knock each other out. So because they were 1, then you divide out. And x minus 5 divided by 2x minus 1. Now keep in mind, we got to go back to our original here, right on the bottom. This is where our restrictions are located. X can't be a half, because that'll make this a 0, and x can't be negative 4, because that'll make that 0. So my domain is x of x such that x cannot be negative 4 and 1/2. And again, doing it in set builder notation makes it easier than interval notation the more restrictions I have. That should do it for notes. This is your assignment for A3. I hope things go well. I've noticed a few mistakes as I was stepping through. If you guys do notice mistakes on things, please let me know, and I'll see if I can get those things cleared up. If there are any other questions, just drop me an email or talk to me in class. Have yourselves a great day, and thanks again for all your work.